Okay, we need to get started today. And before I get into the chemistry, there's a couple announcements. One that I was asked to pass along by a student organization, Alpha Eta Alpha. So they have their annual health panel tomorrow, 6 p.m. in Agnes Arnold, featuring all sorts of pre-health students if you're interested in that. So this announcement's in the notes. You can take a look at that. Now, also some announcements pertaining to the course itself. There will be some disruptions in the regular office hour schedule this week, which I realized I was AWOL last week, so this is poor timing. But this should be the last time that there's any issues with office hours. I just want to make sure you're aware of. So there won't be any on tomorrow, which is Tuesday. I had a grand total of 0 people come today, so I don't think many of you will be disappointed. So I won't be available tomorrow. Some things came up, and I apologize for that. And then on Thursday of this week, the normal ones I won't be there for, but I should be available. I'll have to check my schedule exactly, but I should be available most of the afternoon, like 2 p.m. You know what? I forget my schedule now, so I won't be able to tell you exactly. But there won't be any from 12 to 1 p.m., but probably other times. And what I'll do is I'll probably send an email tomorrow because I have to remind people about some other things that I'm going to be saying today. So anyway, you'll get an email from me about Thursday, but they won't be during the regular times if you're trying to plan for that. I apologize for that. Those are the last disruptions we should have. And then what I'll also do, because the last 2 weeks of the semester, which is next week and the following week after that, the third exam and the final week, are always a busy time for me in the office. I will post a schedule on Blackboard that says exactly when I will be available, so it'll be more than just the normal 1 hour a day, and that way there's no guessing work about whether I'll be there or not. You can just check the schedule on Blackboard and come when you're able to, and I will have to update that if necessary, but I should be able to get it set by the end of this week, and then there won't be any confusion there. And the last thing is that our next class that we meet Wednesday, which is I think I got my dates wrong. This is the 19th, and then the 18th is Wednesday. We're going to do the course evaluations at the end of class, so I hope that you're all able to come and participate. We want to get a nice representative sample of opinions on how I did this semester and other things related to the course. And also there will be a small incentive in the form of a bonus quiz that day, which you will get full credit for just by showing up. So hopefully that encourages more of you to come. And that's going to be happening this Wednesday, as I said. All right, so with that, I'll get into the material for today. So what we started talking about on Wednesday when I wasn't here, but hopefully most of you were able to catch it on YouTube, is that we're talking about condensed phases of matter, and we went into some properties of metals, which is the first class of solids that we'll talk about. There's going to be 3 major categories of solids that we'll talk in detail about. We're going to get 2 of them today. And a lot of these solids that we're talking about are what are called crystalline solids, meaning they have regular structures, and we sort of introduced on Wednesday some of the basic terminology associated with crystalline solids. They're basically regular repeating units of atoms, and you have unit cells that are small parts of that crystal that you then stack in all directions to get the extended infinite structure. Now, what we're going to start out with today is a little bit of background on how we determine the structures of these solids. So how do we know how far apart the atoms are, or what kind of geometric shapes they're arranged into? How do we actually determine that experimentally? This is all going to be background information for the first couple slides. We don't expect to know a lot of these details, but just to get you oriented, and then we're going to talk about some of the features of different types of crystal structures, specifically today for metals, which is the first category of solids we're going into. All right, so what we have is the technique that we use for determining the structure of crystalline solids is called X-ray diffraction. And so as the name implies, you have X-rays that scatter off of the crystal. So you direct an X-ray beam into the crystal, and then it scatters off in all directions. And the reason for this is because the spacing of the atoms in a typical crystal is similar to the wavelength of the X-ray beam. And so because those two are matched up pretty well, you get a lot of diffraction. And when you have diffraction, you have these scattered X-ray beams coming off in all directions. you can have what's called constructive and destructive interference. So some of the waves are going to line up with each other and they're going to reinforce, and you're going to get what's called constructive interference. And then some of the waves are going to line up in such a way that the waves are out of phase, which means the crest of one wave is aligned with the trough of another, and you get what's called destructive interference. Some of these things we sort of talked about a little bit when we were introducing the properties of waves. But in any way, in an X-ray diffraction experiment, you get both constructive and destructive interference. And then this is sort of what the picture looks like down here. So you have your X-ray beam that goes into the crystal, all these beams scatter in different directions, and you're going to have a detector where you're going to see these spots, and those are the spots wherever the constructive interference occurs. Okay? So these spots that we see on the detector plate, which is just in olden days was just a photograph of film. Now we have fancier ways of doing this that are a little bit more computerized, but we still detect the diffracted X-rays, and these spots represent where we have that constructive interference. And then the reason this is important is the position of the spots, how far away they are from each other, what angle they're at. All of that information can be used to then determine the spacing of all the atoms in the crystal, how far apart the atoms are from each other. There's some mathematical equations that relate those. And the main equation that we use in a two-dimensional setting, obviously crystals are three-dimensional, so it becomes more complicated than this, but if we're just talking about a sort of a two-dimensional face of a crystal, what we use is called Bragg's law. And so what we have here is, as I said, we're going to have X-rays coming onto the crystal at some angle, and so that angle is going to be theta, which is the angle of incidence of the X-ray beam onto the crystal. And as we do these experiments, we typically rotate the crystal around in different angles so we can sample a larger space. And so that's the angle that's labeled here as theta. And then what we see here is that as the X-rays come off, they sort of diffract off of these different planes of atoms. So crystals, again, are regular arrays of atoms. You're going to have these flat planes of atoms lined up in all directions. And so distance d here, this d right there, is going to be the distance between planes of atoms, which is ultimately what we want to be able to measure to be able to piece the structure together. And then what we have also, another parameter that's important is this one here, lambda, which is the wavelength as we've defined it before. So it's the wavelength of whatever X-ray beam we use. Most X-ray diffraction experiments use an X-ray source that gives you a wavelength of about 0.71 angstroms, but there are other ones that are different than that. So the wavelength of the X-rays is determined as well. And when you put all this together, and this is called the Bragg equation. It was formulated by a father-son duo. I think they're the only father and son to win the Nobel Prize together, so some quality bonding time over this equation apparently. And what they came up with was that n times lambda, which is the wavelength, is equal to 2d sine theta, where n is some integer value. So in other words, repeated application of the Bragg equation, rotating the crystal around to different angles, sampling different values of theta. You can measure different distances between planes in the crystal, and you can take all those distances and piece them together into a three-dimensional structure. It's a lot more complicated than what I just described, but that's sort of the essence of it. And like I said, we don't want you to be able to know all these details, just to get an idea of how we get these structures. So we use this experiment called X-ray diffraction that gives us the structure of different crystalline solid materials. We're going to talk about structures of both metals, which we'll get to today, and then ionic compounds, which we'll talk about next time. They have some interesting structural features associated with them. Now, the first thing to get into before we talk about the details of the structures is what we're going to be doing in the vast majority of the structures we talk about in details. We're going to be arranging the atoms into a cube. So each unit cell in our crystal is going to be cube-shaped, and then, like I said, to generate the crystal, you take those small cubes and you stack them in all directions. So we're going to have atoms in different positions on the cubes, and based on where those atoms are on the unit cell, they're going to count differently. We want to understand where those different positions are. So there's 4 different possible places on the cube that we can place an atom in our crystal structure. So the first one that I'm showing here is what's called the body center. So that's just taking an atom and putting it right at the middle of the unit cell. Now, as I said, these unit cells are stacked in all directions. So this unit cell is going to be bordered by one on each and every side. But the atom that's in the middle is not going to be on the border between any of those 2 unit cells. It's going to belong exclusively to the cube that it's inside of. So when you have a body center atom, it's not shared by any other unit cell. And so when we count the number of atoms in the unit cell, we just count this as 1. Right, because it's completely in the center of the unit cell, so it's not bordering any of the other unit cells that are surrounding this one, and so we count that as a full 1 atom when we have an atom in the center of a unit cell. Another place that we can put atoms is on the face center. So in this case, as the name implies, we're taking an atom and we're putting it right in the center of one of the square faces on our cube. And if we have this situation here, this face is going to be the borderline between 2 different unit cells. There's going to be one, as it's shown here to the left, that's going to share that same face. So the atom is going to be right on the borderline between 2 of the unit cells. And so when you have an atom in this position, it's shared by 2 unit cells. And so when we're counting it, we're going to count it as 1/2. Because a lot of the things we're going to talk about, a lot of the properties of crystals, things like their density or their packing efficiency, which was something we'll talk about today, a lot of these properties are somewhat dependent on how many atoms are actually in the unit cell. So when we're counting them, we're going to do it in this way. So an atom that's on the face we count as 1/2 because it's shared by 2 unit cells. And then similarly, if we have an atom along the edge, it's going to be shared by 4 unit cells. You have the one that's to the left, the one that's in front, and then the one that comes out in the other direction. So you have 4 unit cells that each share an edge. So think about stacking cubic blocks in all directions. Each edge is going to be the borderline between 4 of those cubes. So an atom on the edge is shared by 4, and that means we count it as 1/4. All right, because there will be some homework questions and things where we'll give you a hypothetical cubic structure. We'll say you have this many atoms on the faces, this many atoms on the edge, how many total atoms do you have? And so this is going to give us an idea of how we count those. And then finally, the last place we can put it is in the corner. In this one, you're going to have shared by 8 unit cells, so we're going to have the 4 that are below or in the same level as this one, and the 4 above as well. So each corner is shared by 8 unit cells. And so we count each corner atom as 1/8. And it's important that we understand this now as we go in to start talking about some of the common cubic crystal structures that we see in metallic elements. Okay, so we have these different positions that we can occupy in a cubic cell, and then we're going to now talk about the different ways that the atoms arrange themselves, different combinations of these positions. So the first one we're going to talk about, which as the name implies is probably the simplest, is called simple cubic structure. Now what we're not going to worry about in this course is trying to remember, so these different structures we're going to give you, each metal on the periodic table has a structure associated with it. We're not going to ask you to remember which metal is which structure. We just want you to understand the basics of them and sort of some of their features. So the way we generate the simple cubic structure, a lot of times we're going to think of these structures as being generated from layers. So we have layers of atoms and we start stacking them on top of each other, and that's going to generate a cubic structure. So we start with one layer. And as you'll see, this layer of atoms that we're using, all of them are touching, but the rows are all eclipsed with each other. So you see this first row is lined up exactly with the second row and the third row and so on. So that's what each layer looks like in a simple cubic structure. And then we're going to just stack those layers exactly on top of each other. So as this picture shows, we just stack subsequent layers exactly on top of the one that we started with. So we stack all the layers directly on top of each other. And then if we pick out a unit cell from this, in other words, a group of atoms that we can just take and then translate in all directions to generate the bigger structure, what we get is called a simple cubic. And as you can see in a simple cubic structure, I think this top view shows it the clearest, you just have one atom in each corner of the cube. So simple cubic, you're just putting, each corner has a single atom in it. There's different ways of showing this. So this one below it is that cube sort of stacked in all directions, as we said happens in the crystal. So the unit cell would just be one of these cubes that were then stacking in all directions. A little bit hard to follow. Let me see. I think I messed that up. So we need a cube. So that cube, something like that, is one of those unit cells. Then we stack it in all directions. And then this one down here is showing sort of a space-filling model. So we know that the atoms, they take up some space with their valence electrons, and they're going to come as close to each other as they can. So in a space-filling model, you can see how the atoms are all touching, but they're all just located on the corners of the cube. Now, one important parameter that we want to talk about then is what's called the packing efficiency. So we can see just by looking at this structure down here with the space-filling model that there's a lot of empty space, especially in the middle of the cube. So we want to know what percentage of the volume of this cube is actually occupied by the atoms themselves. And so we're going to derive that here. The derivations are not going to be something you're asked to reproduce on test, but I think it's interesting and fun, so we'll do it anyway. We just want to make sure we know the numbers and understand the differences between the different structures we're going to talk about. So let's talk about some of the features of this crystal structure. So the first thing that we always want to define is what's the length of one side of our cube. So we know from geometry that a cube is a three-dimensional solid where all the sides have the same length. So let's define that length in terms of something related to the element itself. So if we have this simple cubic structure, we said that each corner has an atom in it. Each atom is going to have some characteristic atomic radius r. And our side length here from corner to corner we're going to abbreviate as A. That's just the sort of standard definition they use when we're talking about crystal structures. So the side length is A, and as we can clearly see in this simple cubic structure, A is equal to 2 times the radius. So as we go from one corner along the side to the next, we see that we go through 2 atomic radii. So this length we can write in terms of 2r, where r is the radius of the atom that makes up the structure. If we want to know what the volume of the unit cell is, the volume of a single cube, we know that that's equal to a cubed from geometry. So again, a lot of this stuff comes from geometry, which hopefully most of you had in high school, but we're not going to hold you responsible for a lot of this, so don't worry about it if you don't. So we can write the volume of the entire cube in terms of the radius of the atom, 8r cubed. We just make that substitution, a equals 2r, and then we cube the whole thing. So that's the volume of the cube. Now we can also think about how many of these atoms or spheres in general are inside of this unit cell. So we know that there's 8 corners in the unit cell, 8 corners in each cube. Each one, as we said, counts as 1/8 of an atom because they're shared by 8 adjacent cells, and that means in that we have 1 atom or 1 sphere inside of our unit cell. So 1 times 1/8, these are all our corner positions, and those are the only positions that are occupied in a simple cubic cell. So we have a total of 1 atom inside of there. Each corner includes 1/8 of an atom. And then finally, if we want to find the total volume of all of the atoms themselves, each atom we approximate as a sphere. And so there's 1 atom, and the volume of the sphere is 4/3 pi r cubed. So that means the total volume of the spheres, or the atoms in the unit cell, is given by 4/3 pi r cubed. And then if we want to find what's called packing efficiency, we're going to take the volume of the spheres, the volume of the atoms themselves. I'm using spheres to represent atoms because they could be something other than atoms. But anyway, in a typical metallic crystal, these are just the atoms that make up the crystal. If we take the volumes of the spheres and divide it by the volume of the cubic unit cell, and then multiply by 100 to make it a percentage, that's what we call the packing efficiency. It's the percentage of the space in the unit cell that's actually occupied by the atoms, the rest of it being empty space. So we just take these 2 volumes, the volume of the spheres, which was given by 4/3 pi r cubed. We divide it by the volume of the cube, which in terms of the radius is 8r cubed. And we can multiply that by 100. A lot of stuff divides out. What we get is pi over 6 times 100, or the number that you should at least be a little bit familiar with, which is 52.4%. So in a simple cubic structure with just a single type of element in there occupying the corner positions, 52.4% of the volume is occupied by the atoms themselves. The rest, about 48%, is all empty space. So we got this number from geometry. Like I said, we're not going to ask you to derive this, but you should be at least a little bit familiar with how the side length relates to the radius, and also this number here, at least in a relative sense, as we start comparing the different structures. So that's the first one we're going to talk about, which is simple cubic, and it has a packing efficiency of 52%. Let's see then how things change if we look at some other configurations, some other types of cubic structures. So the next one we're going to talk about is called body-centered cubic. And again, the name, I think, is pretty instructive of what we actually have. In a body-centered cubic cell, you have each corner position is occupied, and you have one more in the center. So we saw that in the simple cubic, the center of the cube, the center of the unit cell was empty. Now we're just shoving one more atom in there. Now to be able to do that, we have to move the atoms a little bit farther apart. There's not enough space in the center of a typical simple cubic cell to cram another atom in there, so we have to spread things apart. So if we want to think about how we build this structure from layers of atoms, we have to do it a little bit differently. So we start with a layer that has a space in between each atom. So the first layer is going to be, we're going to place the atoms in a layer but with a space in between. In the second layer, we're going to take another one of these and we're going to put it over top of the spaces that were in the first layer. So we're not going to put the two layers exactly on top of each other. We're going to stagger them. So the second layer goes in the spaces that were created in the first layer. So they go over the spaces, and those would be the ones that then would occupy the center of the cube. But these are all the same atoms, and just showing them in different colors so you can clearly see the differences between the two layers. It's not that there's two types of elements or two types of atoms, it's just that we're trying to keep the two layers straight. And then the third layer, we're going to stack that exactly on top of the first. So we stack the third layer such that it eclipses the first, or is exactly lined up with the first layer. In the notation we sometimes use for this, we would call this A-B packing, because we have two identical layers, but we stack the second one staggered from the first. So we stack the second one differently than the first, but then we start going back and repeating after the second layer. So we call it A-B to indicate that after two layers we go back and start repeating that process over and over again. So it's a lot of different ways to think about it, but the one again that's important for you to understand is this picture here, I would say, which is the body-centered cubic cell. It has 8 corners occupied, and then we put one more in the center as well to occupy that empty space. And then again we have the extended structure shown below that, which is just that same body-centered cube reproduced in all directions, stacked in all directions, and then we have the space-filling model here, which shows how the atoms actually come in contact with each other. Now the geometry for this is a bit more complicated because we have this one in the center. So if we want to think about how to get the length of a side, it's not as simple here, because if we go along one length of the side, we don't have two atoms touching each other. We have a little space in between them. So if we go back to this one, you can see that as we go along the side here, there's a little bit of a gap between the two atoms along the side. So the side length is no longer just equal to 2 times the radius, because there's a little bit of a space between those atoms to accommodate the one in the center. So it's a little bit more complicated now. So what we're going to use here is the length of a cube diagonal. We're going to start in one corner of the cube and go completely to the opposite side along the diagonal, the 3-dimensional diagonal of the cube. And from geometry again, if we have a cube diagonal, that diagonal squared is equal to the sum of the squares of the sides, which are all A. So the side length is still abbreviated by A. That would be this length there is A. And the length of diagonal is then D squared is equal to A squared plus A squared plus A squared, or simplified, this diagonal is equal to A radical 3. And then if we want to find what A actually is in terms of the radius, so this diagonal, as we said, is equal to A radical 3. And as we traverse the diagonal, we go through one atom that's in the corner, so we go through one radius. We go through the other atom that's in the center, so that's another 2r, radius. And then we go through the atom that's in the opposite corner, which is another r. So as we go from bottom corner to top corner across the diagonal, we go through 4 atomic radii. One in each corner, and then the one in the center, we have to go through the whole diameter. Okay, so that means that this diagonal D can also be written as 4 times the atomic radius of whatever atom is in there. And so if we solve for the side length A, it equals 4r divided by radical 3. So as we saw before, the radius of, the side length for a simple cube was 2 times r. This one's a little bit more complicated. It's 4 divided by radical 3, so a little bit bigger than 2 times r because of the little space in between. But it still comes from geometry. This time we just had to think about it more three-dimensionally, which I recognize is sometimes a challenge. And then if we're going to count the number of spheres per unit cell, the number of atoms in each cube, what we have is, again, all 8 corners are occupied. So there's 8 corners, and each one, as we said, counts as 1/8. But then the difference here is that we have the body center also includes an atom. So there's one body-centered position, and that counts as a full atom because that one in the center is not shared with any of the adjacent cells. So when we count this up, we would see that in net, the body-centered cubic crystal structure has 2 atoms in it. The one in the center plus the 8 1/8 that you have in each corner. So in that, we have 2 atoms in the unit cell, which means then that the volume of those spheres, the volume of the atoms, there's 2 of them now. Each one still has a volume of 4/3 pi r cubed. That's the equation for the volume of a sphere. So in this case, the volume occupied by the atoms is given by 8/3 pi r cubed. Alright, so we have the volumes that are occupied by the atoms. We have the length of a side, where the volume of the cube is then just the cube of that. So what we can then do is do the packing efficiency. So the packing efficiency is the volume of the atoms, which is 8/3 pi r cubed, as we just said. We divide that by 4 over radical 3 is the length of a side. 4r over radical 3. I should write that more clearly so there's no confusion. 4r divided by radical 3. We cube the whole thing. That's the volume of the cube. So each side is 4r over radical 3. We cube that and multiply by 100 to get it into a percentage. So if we simplify this, we get 8/3 pi divided by 4 over radical 3 cubed, which doesn't simplify in any real way, but if we just want to get this as a number, it comes out to 68%. Alright, so in this case, 68% of the cubic volume is occupied by the atoms. So we see that it's a higher packing efficiency than the last one, which hopefully makes sense, because in the last one we left the center of the cube completely empty. Now we've shoved another atom in there, so we're able to fill up more of the available space. Alright, so this one comes out to 68%, and again, the exact numbers you should be at least a little bit familiar with, but the main important thing is that the body-centered cubic is a more efficient packing than simple cubic. So those are the 2 we've gotten through so far. There's a lot of geometry that goes into getting these numbers, which I hope you find at least a little bit entertaining, but the important thing is the final number that we get, 68%. And then finally, the last one we're going to do then is what's called face-centered cubic, the last cubic structure. So face-centered cubic from a layered standpoint is a little bit more complicated to think about, but the structure itself is not too bad. And so another synonym for face-centered cubic is cubic closest packed. So you might see this terminology in homework assignments and tests. Cubic closest packed, or CCP sometimes. So it's two words that mean the same thing essentially. And this one is referred to as face-centered cubic. So as the name implies, it's a cubic structure. We have atoms in all 8 corners, just like we do for any cubic structure, but now each face of the cube is occupied also by an atom. A little bit hard to see in this view. If you actually go to the bottom one here, I think it's more clear. You have all 8 corners are filled up, and then each of the 6 faces of the cube has one present right in the middle as well. So it's called face-centered cubic. We take a cube and we put another atom in the center of each face. Now the way we generate this is from what are called close packed layers. So if you think about taking a pile of marbles and then trying to stack them together in a layer as close to each other as possible, the way you do that is you lay out the first row of marbles, and then the second row, instead of putting them exactly below that, you sort of line them up with the spaces in the first row. So we call this a close packed layer of spheres or atoms. Oh, don't crash. So we start with a close packed layer. Or again, a close packed layer is just a 2-dimensional layer of spheres put together as closely as possible, where you take the gaps in the first row and fill them in with the second row. So they're sort of staggered like this to fill in as much available space as possible. And then what we're going to do is we're going to stack them on top of each other, and we're going to do this in what's called an ABC or ABCA arrangement. So the first layer, which is shown in yellow down at the bottom here, the second layer we're going to put that over the little small gaps in the first layer. So we're going to stagger the first 2 layers. And then the third layer we're going to put over the spaces in the second layer. So we don't line it up with the first layer, we still put it over the spaces in the second layer. So this first layer we're going to call A, the second layer is called B, third layer is called C because it's still not lined up with the first layer. And then finally the fourth layer here we put back over top of the first layer. So we call this then ABCA packing. So A, B, C, A. So blue is A, green is B, yellow C, and then blue back to A. So these 2 layers, the 2 that I've labeled as A, are lined up exactly with each other. The 2 in between are sort of staggered from that. So we take each layer and line up with the spaces in the previous layer, and then after 3 layers we start repeating that pattern over and over again. So we're going to call this ABC, or sometimes ABCA packing, which indicates that we do 3 layers before starting to repeat the pattern and doing those same 3 layers over and over again. So it's ABCA, meaning that we line up the previous layer with the gaps in the first layer. The third layer gets lined up with the gaps in the second layer, and it's not until after 3 layers that we start repeating that whole process. So it's ABCA, and it's a little bit hard to visualize because what actually happens if we look at these layers here, going from top to bottom, that actually represents the diagonal of the cube. So you have to take this whole thing and sort of twist it over onto its side to generate the face-centered cubic, where again, the opposite corners are made up of the A layers, and then the B and C layers are sort of sandwiched in between along the diagonal. So it's a little bit hard to visualize, I'll acknowledge that. But this is how you sort of reproduce then the face-centered cubic structure. When you take these layers and sort of cant them onto their side, where this is now the diagonal, as we go through the layers, you have corners occupied and then 1 atom in each face. So we're not going to worry too much about the details of the packing, but you should at least know, even if you don't fully understand what it means, that this is ABCA packing, and that generates then a face-centered cubic crystal structure. All right, now going into the geometry of this, it's not as bad as the last one, as it turns out, because here we can just look at the diagonals along a face of the cube. So what I'm showing here is one of the square faces of the cube. So remember, a cube is made up of 6 square faces, where again the side lengths are given by A. And once again, there's a gap in between the atoms that are along each corner, so we can't just have a simple relationship by going along the side of the cube A. But what we do see is as we go through the diagonal of the cube in a 2-dimensional sense now, so we're just going along one of the faces. If I go back to this picture, we're just going along, for example, this diagonal there through the front face of the cube or any of the faces of the cube. The length of a 2-dimensional diagonal is just given by a squared plus a squared equal to the diagonal squared. So that's also from geometry a little bit simpler than the one we saw before, which means we can write the length of the diagonal in terms of the side length A as a radical 2. And then also as we go through this diagonal, what we see yet again is that this diagonal, which is equal to a square root of 2, can also be written in terms of the radius of each sphere. So as we go across the diagonal, we go through one radius to get there. We go through the face center, which is two more radii, so that's r, and then a fourth one to get to the corner. So this time it's a two-dimensional diagonal, but it's the same story as before. As we go from one corner to the other, we traverse through 4 times r, 4 times the atomic radius, to get across there. Which means then that in terms of the radius, the side length A is equal to 4r over radical 2, which is equal to 2 radical 2r. So even bigger in terms of, or even a larger factor times the atomic radius in this case, 2 radical 2r. So that's the length of one side of the cube. Now we have to count the number of atoms or spheres in the unit cell. That's the next step of this, as we see. So still we have 8 corners occupied, so that's 8 times 1/8 for the corners. So all of the cubic structures have the corner positions occupied. That's the same for all of them. But then this one, as we said, the faces are occupied as well. And there are 6 faces in a cube. So count along the sides, and then one on top and one on the bottom. So that's 6 total faces. And as we said at the beginning of this, all of these face positions count as half of an atom, because they're shared by 2 adjacent unit cells. So when we add these up, 8 times 1/8 plus 6 times 1/2, there's a total of 4 atoms per unit cell in the face-centered cubic structure. Okay? So one unit cell is going to now have 4 atoms in net, which means that the volume of those atoms is given by 4 times 4/3 pi r cubed. Or 16 over 3 pi r cubed. So that's the volume occupied by the atoms. And then once again, the packing efficiency is going to be just the ratio of those two multiplied by 100. So it's the volume of the atoms themselves, which is 16 over 3 times pi r cubed, in other words 4 spheres, divided by the volume of the cube, which is that number, the length of a side, also cubed. So 2 radical 2r whole quantity cubed times 100. No real way to simplify this, but what we get numerically is 74.0%. So we see that this is the most efficient packing arrangement for a cubic crystal structure. We went from 52% with simple cubic, 68% with body center, and now with face-centered cubic, we've gotten the packing efficiency up to 74%, and that's the highest that we'll see for any of these cubic structures. All right, so any questions on those cubic structures or the various aspects we've talked about before I move on? Okay, so what we're going to now talk about is the one that's not cubic, which this one we're not going to go into as much detail on because it's a little bit harder to visualize, but it's an alternative form of close packed arrangement called hexagonal. So the only difference here is that if we look at the layering of this, instead of doing A, B, C packing, where we eclipse the third layer, where we eclipse 3 successive layers before repeating, we only do 2 layers here. So we're going to put the A layer down. We're going to put the B layer in the sort of crevices or the little triangular holes in the first layer, and then we're going to put the third layer on top of the first layer. So it's just going to be A, B, A packing. So the yellow layers are A, B, and then A again, or from the side view, A, B, A, B. So we just alternate 2 layers in this case instead of 3. We don't have 3 staggered layers. We just have 2. So this is going to be, this hexagonal close packed structure is generated by what we call AB or sometimes ABA packing, meaning that it's 2 layers that then repeat themselves as opposed to 3. The number of atoms in a hexagonal unit cell is a little bit, again, more complicated, so we're not going to worry about all the details. But if we want to count the number of atoms, this whole piece here is what we're going to count as a whole unit cell. And so what you have then is each of these 6 atoms on the top and bottom, so there's a total of 12 that sort of form this hexagon. Those are shared by 12 unit cells. the 6 that border each of those around there, and then one above, one below, or one below in the same layer. We have 3 that are right in the center of the unit cell. So these 6 atoms on the top and the bottom sandwich a layer of 3 that are completely enclosed in the unit cell. So we count those 3 individually. And then we have this top and bottom one here, which there's one in the center on the top, one in the center on the bottom, that are shared by 2 unit cells. We count those as a half. So the counting is different. We're not going to have you be responsible for how you count hexagonal positions. But what you should realize or should remember is that there are 6 atoms in the unit cell now. So that's what we get for hexagonal, is a total of 6. 12 times a 6 is 2, plus 3 is 5, plus another 2 times 1/2, total of 6. And again, that's a little bit harder to see here, but if you have this hexagonal structure, there's 12 that are shared by 6 other cells, and then there's going to be 3 in the middle, and then 2 on top and bottom. And then we're not going to derive this because, again, it gets excessively complicated when you're dealing with something that's not a cube. But the packing efficiency for this, we're still using we're still using close packed layers. So we still have these close packed layers of atoms where the spheres are as close to each other as possible. So the packing efficiency, not surprisingly, is exactly the same as what we got before. So the take-home message for all of this is that there's 2 ways to generate close packed structures. Either ABC stacking, which gives you the face-centered cubic array, or if you do AB or ABA packing, as we call it here, you get the hexagonal close packed. Both of those are 2 different ways of generating these different close packed structures, but they both have identical packing efficiencies because they're both made up of these same types of layers of atoms where the atoms are as close to each other as possible. Alright, so again, we're not going to do a lot with hexagonal because they're more complicated, and we're not going to see any ionic compounds, for example, that are based on the hexagonal, but this is just an alternative form of the close packed structure. Now the last thing we need to talk about, the last sort of structural parameter we're going to want to become familiar with, is what's called the coordination number for all of these. All right, so this is the last parameter we're going to deal with. And so what coordination number is the number of nearest neighbors that each atom has in the structure. Or another way to think about this is the number of other atoms that an atom in the structure is touching. Right, not counting itself, obviously, but how many other atoms are directly next to that single atom in each structure. And the coordination number for every atom in the structure is the same. They're all equivalent positions, so there's only one coordination number you have to worry about for each structure. So let's talk about how we get that number for these different ones here. The one that's, I think, pretty easy to see is simple cubic. So in a simple cubic structure, if we look at, again, these were the layers of atoms that we had. Let's figure out how many atoms are bonding, or sorry, not bonding to, but are neighboring that single atom there. So in the same layer as this one, we have 4 atoms that are directly adjacent to that one. So that's 4 things that are touching that atom. And then if you think about how we stack the layers, there's going to be one right above that's on top of it, and one right below it that's below it. So there's one more in each direction then as we stack the layers, one above and one below. So the total then is going to be 6. The coordination number for a simple cubic structure is going to be 6, meaning that each atom in the structure is bounded by 6 others, is touching 6 others. 4 that are in the same layer, and then 1 above and 1 directly below as we stack the layers. So that's what we get for simple cubic. The one that I think is easiest to visualize is the body-centered cubic. So if we just focus on the central atom here in the body-centered cubic structure, we see that it's boundaried by all of the corner atoms. Okay? So how many corners are there? There's, of course, 8. 1, 2, 3, 4, 5, 6, 7, 8. So each atom in a body-centered cubic structure has 8 nearest neighbors, meaning the coordination number is 8. And it's obviously easiest to see for this center one here, but if we extend this in all 3 directions, every single atom in the structure will be bounded by 8 others. So it's not just the one in the center. All of these are equivalent in all these structures, and so the coordination number for every atom in a body-centered cubic is 8. And then finally, the next one here, which is a little bit difficult to see is the face-centered or hexagonal structures. They have the same coordination numbers, but we'll talk about it in the context of body-centered cubic here, just to be clear. So what we have in this case is, and I think I accidentally deleted a picture that would have been helpful, so I'm sorry about that, but we can still get it anyway. So let's focus on this atom here, and let's figure out how many nearest neighbors it has. So in the same layer, it has these 6 that are all surrounding it. And then if we look at that atom, there's also then going to be 3 in the layer below it that it's sort of sitting on top of. As we said, we line up each layer in these structures sort of on top of the cracks in the previous layer. So below this one here, in this yellow layer as it's drawn, we have, I'll count them sequentially. So we have 7, 8, and 9. So 3 more atoms that are touching it in the layer below. And then we have the same thing in the layer above. So if we're focusing on this one here again, in the layer above it, which is shown in green, a little bit hard to see, we have 3 more, 10, 11, and 12. Alright, so a little bit hard to visualize in this case, but the coordination number for the body-centered cubic structure, the cubic close-packed arrangement, is going to be 12. 6 in the same layer, 3 above, 3 below. Total of 12 that are going to touch each one. So we see that as we go through these different structures here, the coordination number increases, and so does the packing efficiency, and that should hopefully make sense, because if we're cramming more atoms around each one, we're going to have them occupying a more efficient space and have a greater packing efficiency. So as I said, a lot of those details are a little bit tricky, a little bit things that we're not going to really go into a lot of depth in when we ask you questions on homework assignments and tests. You'll get a good flavor for the types of questions we'll ask you as you do the homeworks. But what's going to really be beneficial to you is if you can just learn this table. Understanding where these things come from is still going to be helpful and important, but if you can learn the information on this table, you should be pretty much good to go for this section as we talk about metallic structures. As I said, we're not going to go into a lot of depth and a lot of detail on these types of questions. We just want you to know the basics. So what we have are, again, 4 different structures that we've talked about: simple cubic, body-centered cubic, face-centered cubic, and hexagonal. 4 unique structures. And some of them have some synonyms associated with them. So simple cubic is also referred to as primitive cubic. So again, we just don't need to be tripped up by terminology. So simple and primitive mean the same thing in the context. It just means the structure where you have each corner position occupied. Body-centered cubic doesn't have another name associated with it, but we do use the abbreviation BCC sometimes. Body-centered cubic, pretty obvious. And then face-centered cubic, as we said, we can abbreviate it as FCC, or it's also called cubic close-packed, CCP. So both of those all mean the same thing. And then finally, hexagonal is also referred to as hexagonal closest packed, or HCP. So these are abbreviations that we just want you to be a little bit familiar with. Now the 3 things you're going to want to know about each of these structures are the number of atoms per unit cell, which you can memorize, or as long as you know the rules for counting and where each atom is, you can derive them as we did. That's, I think, the easiest part. So the number of atoms per unit cell, as you saw for the simple cubic, it's 1. You just have 8 corners occupied. For the body-centered cubic, there's going to be 2, 8 corners plus 1 in the center gives you a net of 2. Face-centered cubic, as we saw, has 4 atoms per unit cell. 8 corners and 6 faces is a net of 4. And then finally, hexagonal, which was a little bit hard to count, we saw had 6 atoms per unit cell. So those are the number of atoms per unit cell as we count them up using the rules we learned at the beginning. The number we just derived is coordination number, and it tends to increase as the packing efficiency increases. So simple cubic has the smallest coordination number of 6. As you saw, body-centered cubic, you have 8 nearest neighbors. And then face-centered cubic and hexagonal both have 12 nearest neighbors. Okay? So that's the numbers for coordination. And then finally, packing efficiency, the number we derived using sort of a flashback to algebra class from, not algebra, geometry class from high school. The packing efficiency were these numbers that represented the percentage of the total volume occupied by the atoms. And we saw that it also sequentially increases as the coordination number goes up. So 52.4% for simple cubic, the lowest efficiency, 68% for the body-centered cubic, and then the 2 close-packed arrays, the face-centered cubic and the hexagonal both have identical 74% packing efficiencies. All right, so that's sort of the numbers that we want you to know, the sort of things we want you to be able to learn about these structures. So any questions on what I talked about or what we expect you to know about this before I move on? So the next thing I have is one example problem, which it's a little bit more difficult than we'll ask you to do. That doesn't mean it's not valuable, of course, because it shows us how we can use the things we learned about these crystal structures to predict physical properties, one of them being density. Okay? So we know the density is defined as mass divided by volume. If we know what the crystal structure of a metal is, if we know, in other words, which of those cubic positions are occupied, what are the lengths of the cube, the size of the unit cell. If we know all that stuff about the crystal, we can predict what the density would be. So let's look at the metal sodium. It crystallizes in a body-centered cubic unit cell, and the side length is 429 picometers. Again, very small for each unit cell because it's only made up of a few atoms. And we want to know what the density of sodium is in grams per cubic centimeter. All right, so we know the definition of density is mass divided by volume. So what we want to do is, using the information that we have, we know that it's body-centered cubic, and we know the length of a side is 429 picometers. With those two pieces of information, we want to calculate the grams of sodium, the mass of sodium that's in the crystal, in the unit cell, divided by the volume in the correct unit of centimeters cubed. And we're going to do this for one single unit cell. Okay? So let's think about how we do this. The first thing we can do is find the mass of sodium, and that's going to be determined by how many sodium atoms are in this structure. So going back to what we learned earlier, to the table I just wrote, we saw that each body-centered cubic structure has a total of 2 atoms per unit cell. So in one unit cell, we're going to have 2 sodium atoms. We have, again, the 8 corners are 1/8 occupied, and then we have the 1 in the center for a total of 2. And how do we figure out what the mass of 2 sodium atoms is? This is stuff that we've done way back in chapter 5. So if we have 2 sodium atoms, we can convert that to moles using Avogadro's number. So there's going to be 1 mole per 6.02 times 10 to the 23rd atoms. And then if we have moles of sodium, we can calculate the mass using its atomic mass. So from the periodic table, the atomic mass of sodium is 22.99 grams per mole. So when we work this out, what we get is that each unit cell has 7.64 times 10 to the minus 23rd grams. Okay? That number seems wrong. Maybe that's right. Yeah, I think that's right. All right, so I thought it was off by maybe a 1 order of magnitude, but I don't think it is. Anyway, so that's the mass we get by just converting 2 atoms of sodium into a gram amount using molar relationships that we've already learned. And then if we want to find the volume, we just need to take the side length, which is 429 picometers, and cube it. So in terms of picometers, that's 7.90 times 10 to the 7th cubic picometers. Now we want the density to be in grams per cubic centimeter, so we have to now do some unit conversions to get this into the right units. So sorry, that should be volume in picometers cubed. And then if we want to do that in centimeters cubed, we just have to convert it. So we have 7.90 times 10 to the 7th cubic picometers. And then I don't know the conversion to go directly from picometers to centimeters, so I'll do this in 2 steps. A picometer is 10 to the 12th, or 10 to the minus 12th. So 1 meter is 10 to the 12th picometers, so that's going to get us into meters. Because it's cubic picometers, we have to cube that conversion factor. So 1 meter cubed is 10 to the 12th cubed picometers. And then that gets us into cubic meters, and then to go into cubic centimeters, we have 100 centimeters per 1 meter. That's conversion factor. We should definitely know. We have to cube that whole thing as well. Alright, so all the units cancel out. Now we're in cubic centimeters. So it's just going to change the order of magnitude, of course. It's not going to change the number, but it's 7.90 times 10 to the minus 23rd cubic centimeters. So that's the volume of the unit cell in cubic centimeters. So again, an extremely small quantity because it's just a few atoms. And then if we want to find the density, we just have to divide the two. So the mass we saw was 7.64 times 10 to the minus 23rd grams. The volume in cubic centimeters was 7.90 times 10 to the minus 23rd centimeters cubed, and that comes out to 0.967 grams per centimeter cubed. So that's the number that we get using the crystal structure. Going to our most trusted source of information, Wikipedia, for better or for worse, although I do trust most chemistry information on there, it's usually pretty accurate. The density that we find for this sodium in real life that we can measure separately is 0.968. So we lost something in rounding, but as you can see, it's extremely close to the density we get from a measured value. So using crystal structures, one thing we can do is calculate density. This is a little bit beyond what we're going to ask you to do on homework tests and homeworks and tests. We're not going to ask you to calculate density in this way, but you can hopefully understand and follow what I did here, which is if we know how many atoms are in a unit cell, we can figure out the mass that's in there, and then we can use simple geometric relationships to find volume, and then the ratio of those two gives us density. Alright, so questions on metallic structures. So the next thing we're going to talk about today are what are called network solids. We're not going to go into a lot of details on the structures of these as we did for metals. We're going to go back and when we do ionic compounds, we'll see a lot more detail. But for network solids, we just want to understand what they are and just a few things about some of their properties and some of the differences between them. So first, let's define what a network solid is. These are extended solids they're formed by covalent bonds. So they go on in all directions, infinitely, but they're formed by covalent bonds as opposed to metallic or ionic bonds. And what you can think of them as infinite molecules. So we know that molecular compounds, covalent compounds, are sort of synonymous as we thought of them earlier in the course. But if you just take covalent bonds and you just extend them in all directions, you get these network solids, which can be thought of as just infinite molecules. Okay? And there's two types of network solids, as we'll see. There's network atomic solids, which are just made up of one type of atom. These are some of the elements would fall into this category. The two on this slide being examples that we'll get into, as well as silicon. So a lot of things that are sort of in that part of the periodic table, group 4, the carbon group, a lot of those are considered network solids. They're formed of one type of atom. And then we'll also see there's what are called network covalent compounds, which are compounds, two different elements in the structure, two or more different elements, and those can also form these network solids in some cases. So what you have in a network solid, as I said, is just covalent bonds going on forever in all directions. And one example is diamond. So a diamond is just a tetrahedral carbon. So if we look at this carbon atom here, it's bonded to 4 nearest neighbors in a tetrahedral fashion. But these don't terminate. They go on in every direction. So it's bonded to these 4, but then these 4 carbons are bonded to 3 other carbons in the other direction. It just builds this huge network of covalent bonds that goes on forever and ever. But each individual carbon atom is still tetrahedrally coordinated by 4 others. We just focus on one atom. Now, because it's tetrahedral, what's the hybridization of each carbon atom going to be? Review. sp3. So these are all sp3 hybridized carbons. And because it's sp3 hybridized, do we have sigma bonds, pi bonds, or both? Yeah, all sigma, right? So there's nothing different about this just because it's a network solid. If it's sp3 hybridized, we can only have sigma bonds. Remember, we would need unhybridized p orbitals to make pi bonds. So in the structure of diamond, each carbon is tetrahedrally coordinated. You have these really strong sigma bonds going in all directions, and then those go on forever and ever. So that's the structure of diamond, a little bit about it anyway. And then the other major form of carbon, actually the most abundant form, is called graphite. And so graphite is consisted of hexagons, but they're all, again, they go on in all directions, or at least in 2 dimensions. So as you can see, each of these layers you have a hexagon of carbon atoms, and then they're fused to other hexagons in all directions. You form these sort of sheets of carbon atoms that are made up of these little hexagonal building blocks. And these layers are then stacked with each other. Now, each atom in the structure, if you can look at it closely, you'll see that if we focus on one of these carbon atoms, let's say this one here, it forms bonds to 3 neighboring carbon atoms. So if it has 3 electron groups, what's its hybridization going to be? sp2 hybridized. So that's the big difference between diamond and graphite, is just the hybridization of the carbons. They're sp2 hybridized, and that means we have sigma and pi bonds. And again, because they're sp2 hybridized, they form these flat layers, because sp2 correlates with the trigonal planar geometry. So if each carbon is trigonal planar, you form this whole extended layer of them, and then you take those 2-dimensional layers and you stack them on top of each other to get the actual structure of graphite, where there's no actual bonding between the layers. They're just sort of held together by intermolecular forces, the London dispersion forces that we talked about on Wednesday of last week. So that's the difference between diamond and graphite. When you have another term that I just want to introduce quickly, if you have 2 forms of the same element, we call those allotropes. So diamond and graphite are considered allotropes of carbon. They're both made up exclusively of elemental carbon, but they have 2 different structures. And because of their 2 different structures, they have very different properties. So again, a key part of studying the structure of molecules and now the structure of extended solids is to understand how these different structural things affect the properties of the elements and compounds. So if we compare the properties of diamond and graphite, we see that there's some pretty big differences between them. So if any of you, well, I'm sure you've all seen diamonds before. Maybe you own one yourself. And we know that diamonds are very hard materials. They're one of the hardest materials known. They're colorless. And from an electrical standpoint, they're insulators. So they don't conduct electricity at all. Okay? And then if we have graphite, the properties are a lot different. So graphite is found in a lot of, what we call pencil lead is actually a lot of graphite. And so graphite is soft and slippery. It's black in color, as we know. And in terms of electricity, it's a conductor. So by changing the structure of carbon from tetrahedral sp3 to this sp2 hybridized flat sheets of graphite, we change the properties a lot. And if we think about the structure, we can sort of understand that. And what we want to introduce now is what's called band structure. So we learned on Wednesday about metals and how they have these loosely held electrons that are free to move around the structure. That's what gives them their high electrical conductivity. In contrast, if we have an insulator like diamond, what we have is this situation here. So we're going to talk about what's called band structure. When you have these extended solids, remember we talked about in Chapter 4 molecular orbital theory. If you take 2 atoms and bond them to each other, you get bonding molecular orbitals, you get anti-bonding molecular orbitals. Bonding being lower in energy, anti-bonding higher in energy. When you have atoms that go on in all directions, you get the same story. So if we draw sort of a qualitative energy level diagram, when you have diamond, you have your lower energy filled molecular orbitals. We call this the valence band. And because diamond has, an infinite number of atoms in it, or a huge number of atoms in it, we don't get really discrete energy levels. We get a bunch of bonding molecular orbitals that are just really close in energy, so they're all stacked together into what we call a band. So there's basically no energy gap because there's so many of them that are all, together. And then if we have the empty molecular orbitals, the anti-bonding orbitals, those are going to be separated by a large energy gap. So in any insulator, this is what you have. And we call these empty MOs the conduction band. And in any insulating material, which is what I'm showing here, you have a large gap between the filled and empty MOs. And because of that large gap, the electrons are not free to move around, and so you get insulating behavior. The electrons are sort of stuck in the valence band. They're not able to easily move to the conduction band, so you don't get any conduction of electricity. The electrons are more or less stuck in these filled MOs. And the reason you have this in diamond is because you have all sigma bonds. We know that sigma bonds are really strong bonds, and so you get very large separations between the bonding and the anti-bonding orbitals. We saw that in the context of just simple MO diagrams earlier, that if you have sigma bonds, the bonding and anti-bonding spread apart far because there's a very strong interaction. So that's what we have for insulators, which is what most nonmetals are. But then if we have the band structure of a conducting solid, like graphite, so metals or graphite is an example that has this basic structure. What we have is that your filled MOs and your empty ones have no gap between them. So you have your filled conduction band, your valence band, then you have your empty conduction band. And these have no gap between them. All right, and that's what you have in a conductor. Because the filled and empty MOs are right next to each other in energy, the electrons are free to move around between the two levels, and you get this easy conduction of electrons through the structure, which leads to electrical conductivity. And the reason this happens in graphite is because in graphite, the valence orbitals there's a lot of pi bonding, right? We have pi bonds. Pi bonds are weaker than sigma bonds, which means that the bonding and the antibonding orbitals don't spread apart as much, and they actually end up coming and being right on top of each other. So that's the difference. The sigma bonding in graphite gives you a large gap between the bonding and anti-bonding orbitals. The pi bonding in graphite, the sigma bonding in diamond gives you a large gap. The pi bonding in graphite makes the two on top of each other, and you get differences in electrical properties because of that. All right, so that's what we want to talk about with respect to band structure. And then in between these, we have what are called semiconductors. So the classic example of a semiconductor is silicon. So if we ask you on a homework or test question, which of these elements is a semiconductor, silicon and germanium are the two big ones that you should know. So those are two semiconducting elements, and what it means is that their band structure is sort of in between an insulator and a conductor. So you have a small gap between the valence and the conduction band. So they're not right on top of each other like you have in a conductor, but it's not a huge gap like you have for insulators. All right, so your valence band and your conduction band there's sort of an intermediate gap between them, which is why we call these semiconductors. And the big difference between conductors and semiconductors is that unlike conductors, or metals in general, which are all conductors, when you have a semiconductor, the conductivity increases with temperature. And that's because as you increase the temperature, you're able to get more electrons with enough energy to jump from the valence band to the conduction band. So anytime you're going to conduct electricity, you need electrons moving from filled orbitals to empty orbitals, the filled orbitals being the valence band, the empty orbitals being the conduction band. And when you have this sort of intermediate gap between them, the higher the temperature goes, the more electrons that have enough energy to jump to that higher band. So that's what a semiconductor is, and the band structure is sort of intermediate, where you have a small gap between the two bands. Now there are also two types of other semiconductors. So silicon and germanium are what we call intrinsic semiconductors. Just as a pure element, they have a band structure that's sort of intermediate and allows you to observe this semiconducting behavior, which again is in between insulating and conducting. But then the other types of semiconductors are called doped semiconductors, and there's two types we want to be familiar with, N-type and P-type. So in an N-type semiconductor, you dope with extra electrons. And what doping means is you replace some of the atoms with another element. So if we go to the periodic table real quick, and so we see that one of our intrinsic semiconductors is silicon, as we said. So silicon is group 4A on the periodic table, atomic number 14 there, right under carbon. And so if we want to make an N-type semiconductor, we're going to dope it with extra valence electrons. So one way to do that is to replace some of the silicon with an element from group 5, for example, arsenic. So very common what's called N-type semiconductor is what's called arsenic-doped silicon. You take silicon, you just add in a little bit of arsenic into it to give it a little bit of extra valence electrons. So an example would be what's called arsenic-doped silicon. And so in this situation what you have is you have your valence band and your conduction band from the main element, silicon in this case. With some intermediate gap in between them. But then because you've added in these extra valence electrons from the group 5 element, arsenic, so again, arsenic has 5 valence electrons, silicon has 4, all of the valence orbitals are filled because of the 4 valence electrons from silicon, and you have to find a place to put the extra ones. So you introduce these new bands that are close to the conduction band where your extra valence electrons go. So you often show these as little dots. These are the extra valence electrons. And so these extra valence electrons end up in orbitals that are very close to the conduction band. And that means it's very easy for them to move into the conduction band and to have electrical conductivity. So in a doped semiconductor, what you're doing is you're introducing new valence electrons in an N-doped semiconductor that are very close to the conduction band, and then those electrons are then responsible for the conductivity in your solid. So this is what's called an N-doped semiconductor, an N-type semiconductor, which has extra valence electrons. And then the other type is P-type, and as you might guess, this one we're going to dope it with fewer valence electrons. So if we take silicon and we dope it with a group 3 element, the classic example being boron. So silicon is group 4, boron is group 3. So if we have boron-doped silicon, we're introducing an element from group 3 that has 1 fewer valence electron. And so because of that, we still have our valence band and our conduction band in this material. And these bands, again, are defined by the main element, silicon, but we put a little bit of boron into there. Boron has fewer valence electrons than silicon, so we're not able to completely fill the valence band. We don't have enough electrons to completely fill our valence band, so we introduce these holes in the valence band. I'll draw these in blue to keep the color coding consistent. So these are positively charged holes that we introduce into the valence band. And so by doing this, again, we have now empty spaces in the valence band. Electrons from the valence band can move into those empty spaces, and then that gives you the electrical conductivity. So basically, in this case, we're just removing electrons from the valence band, giving then the presence of some empty orbitals that electrons can move into and give you semiconducting behavior. So it's two different mechanisms, but it's the same thing. You're just introducing a way for electrons to easily move from filled orbitals into empty orbitals, and we call that N-type and P-type. All right, so any questions on band structure? All right, the next thing we're going to talk about, which I think is the last, is what's called a network covalent compound. So the ones we've talked about so far, diamond, graphite, which are two forms of carbon, and then we just talked about the semiconducting elements, primarily silicon and those ones. Those are all called network atomic solids. So they're network solids, and they're formed of one type of atom, so they're just elemental solids. But then there's also what we call network covalent compounds, which are covalent compounds that have, again, this sort of network covalent arrangement, covalent bonds that go on forever in all directions. So let's compare two compounds here, CO2 and SiO2. So both of these are a group 4 element, carbon or silicon, bonded to 2 oxygens, or at least that's the structural formula for them, the compositional formula. So we remember CO2, which we've talked about a lot in the context of VSEPR, polarity, all those stuff. It's a linear molecule, discrete molecule. We know that CO2 is a gas, and it has 2 sigma bonds, 2 pi bonds, and it's nonpolar. And it's a gas, okay? So I think we're all familiar with CO2. Now what if we go to SiO2? So let's just replace the carbon with silicon, and things change a lot when we do that. And the reason for this is, remember that in carbon we're using 2p orbitals to form the pi bonds. When we go down to silicon, which is in the row below carbon, we're now using 3p orbitals to form the pi bonds. So the silicon's 3p orbitals, they end up forming really weak pi bonds with oxygen. So if we wanted to form a structure like this, it's no longer favorable to do that because the pi bonds in that are very weak. And again, atoms want to make the strongest bonds possible between them. That's what gives us the most enthopically favorable or the most enthopically stable compounds. So silicon 3p orbitals form really weak pi bonds, so they don't do that. Instead what they do is they form a network solid where you have silicon that's going to be tetrahedrally bonded by 4 oxygens. And then each of those oxygens is going to be bonded to another silicon. I should draw that angle a little bit better. That should be more up like this. But anyway, each oxygen is bonded to another silicon, and then each silicon is bonded to 3 more oxygens. So this one would be something like this. And then you have another silicon and more oxygens and so on. So just this network of silicon-oxygen bonds that goes on forever and ever. Okay, so kind of like we saw in diamond, which was a network of carbon-carbon bonds. This is just a network of silicon-oxygen bonds, and it just goes on forever and ever. So what you have are these SiO4 2- tetrahedra, and they extend infinitely. And then how do you balance the charge? Basically the end ones, the ones on the surface, are either capped with usually just hydrogen protons to balance the charge that you have on the surface, or you would have like some sort of alkali metal cation or something that's in there. But in native SiO2 silica, you would just have protons capping or other weird things that happen at the surface to balance the charge. But each of these is this SiO4 2- tetrahedron, and they're all linked together in all directions. So that's what you get for SiO2. And because it has this network covalent bonding, this really strong covalent bonding in all directions, the properties of SiO2 are way different than CO2. So SiO2, instead of being a gas, it's a hard but brittle solid. You know, hard and brittle sound like 2 different things. Hard meaning that it can scratch things pretty easily, but brittle being that if you try to shape it, it actually just crumbles. It's not moldable like you have for a metal. So it's a hard, brittle solid, and we see SiO2 a lot in our daily lives. So sand contains a lot of SiO2. Glass is another form, an amorphous form of SiO2. But both of these very common materials contain SiO2, which, as we know, has very different properties than carbon dioxide. So by changing to this network covalent bonding arrangement where you have strong covalent bonds in all directions in your material, you change the properties quite a bit than when you have CO2, which has discrete molecules that are nonpolar and have very weak forces of interaction between them. All right, that takes us to the end today. Again, Wednesday we'll have a little bit of a shortened lecture to account for the bonus quiz and the course evaluations, but we'll get into ionic compounds starting then.